we understood any process, we understood any process. This is a process. This is a process. This process contains some stages. Okay, some stages. What are the stages we understood? That is, new state will be there. New state will be there. Then after ready state will be there. Okay. Like this, we have a next running state will be there. Okay. A running state will be there. Okay. So this is new state means from the beginning. Whenever the process starts, its execution time, that that step is called new state. Okay. Likewise, we have running state, ready state, okay, exit state, waiting state. Again, ready state, we have like the states we already discussed about them. So in that, the short-term scheduler is changing the ready state to the running state. So it is changing its ready state to the running state. Then that type of the type of change, okay, based on this type of change, based on this type of change, it can increase the CPU scheduler. No, it is increase the system performance. Increase the system performance. This is the short-term scheduler. Okay, it selects the process from the multiple processes. Okay, here process means what? One kind of job. You can understand. Here process means a job, some task, job. It selects a process from the multiple processes that are in ready state. Okay, that are in ready state. That are ready state in order to execute it. Okay, in order to execute it. Okay, and it's also allocate CPU to one of them. That is from the multiple processes. From the multiple processes, it selects one process. See, there are in the CPU, there are multiple processes are there. In that, it will select one process, okay, and it will send to CPU scheduler. It will send it to scheduler that send it to scheduler to allocate CPU to allocate the CPU time. So it allocate the CPU time. This is a CPU. This is a CPU. So this is the process. It is sending. Who is sending here? Short-term scheduler is sending to the CPU, asking the CPU that allocate the time to execute this process. Okay, to execute this process. So this process will be executed as it is short-term scheduler. This process will execute within the less time. So that is, it is faster than the long-term scheduler. That is the reason. Whereas long-term scheduler will take more time and the short-term scheduler will take less time. That way, the that way we are thus it is increasing the system performance. The CPU scheduler increasing the system performance. Why means because of this the reason. Because the short-term scheduler executes the process within less time. For the long-term scheduler, execute the process in more time. That will take more time, that will take less time. Okay. The short-term scheduler, long-term scheduler, and it is also called a dispatcher. Here is faster than the long-term scheduler. Who is faster than the long-term scheduler? Short-term scheduler is faster than the long-term scheduler. So this short-term scheduler is also known as dispatcher and is also called what? Dispatcher because as it makes the decisions and which the process will be executed next. So very quickly it is selecting the processors. The short-term scheduler is selecting the processors. So that is why this is called dispatcher. Okay. So this is about the short-term scheduler. Now see, next one is what medium-term scheduler. Next one is medium-term scheduler. Okay. Yeah. Next one is medium-term scheduler. What is a medium-term scheduler here is it removes, who is removing medium-term schedule? It is removing the processes, okay, from the memory. And why it is removing? Because it is a part of the swapping. Okay. There is a memory. Okay. There is one more memory like this. Swapping means here is one. This is a process. This is process. Here P2 is there. This is process. P1 is there. Here swapping means the P2 will come to here. The P1 will go to here. Okay. That is called swapping. So here the medium-term scheduling is removing the processes from the memory and is part of the swapping. Okay, this scheduler is removing the processes, these processes from the memory. It will remove from the memory. It is part of the swapping. Swapping means one process will copy into the another will copy into the another. This is swapping. And swapping is necessary to improve the process mix. Okay, it is important as it is doing like that. Next one, when running processes makes an IO request. It will make an IO request for every process execution. Any scheduler will make the IO request. Okay. Now these are all the classification of the process scheduling. Now there is a difference between long-term scheduler, short-term scheduler, and medium-term scheduler. Now observe that differences on the screen. Observe the differences on the screen. Are you able to see the screen? Just look at the that points. Yeah. Now there is a difference between the schedulers. See here, long-term scheduler is a job scheduler, and short-term scheduler is called a CPU scheduler. And medium-term scheduler is having the swapping. Swapping scheduler we call. It is a part of the scheduling. So it is called swapping scheduler. So this is other names for these schedulers. Long-term scheduler is nothing but a job scheduler, and short-term scheduler is nothing but the CPU scheduler, and mini-term scheduler is nothing but the swapping scheduler. So this is the meaning of this. Yes, it's a one point. Next point. The long-term scheduler is slow in the speed. It takes little bit more time. Take little bit more time. And short-term scheduler will take less time because it is very fast. Switching between the processes, it is very fast. The medium-term scheduler is speed is between the other two. Okay. That means it is a moderate. It is neither speed nor fast nor slow. Next one, you see, it controls the degree of multi-programming. What is multi-program? We have discussed it is who is controlling long-term schedulers controls the multi-program. And whereas short-term scheduler, it provides less control over the degree of multi-program. So short-term scheduler is not have control on the multi-program. Long-term scheduler is having the control on the multi-programming. And medium-term scheduler reduces the degree of multi-program. That is the moderate. It is. What is multi-programming operating system? We have discussed in the beginning of the classes. Next one, fourth point is absent or minimal in the time sharing, long-term scheduler. And the short-term scheduler, minimal in the time sharing. Okay. Then the other one, the, that will be part of the time sharing of the system, medium-term scheduler. Okay. The next point is here it will long-term scheduler selects a process from the pool and loads into memory for execution. Pool means pool contains so many processes to be executed like this. This is the pool of processes. So that is, it will take more time to execute. Next one, short-term scheduler selects processes that is ready for execution. So what are the states of the process we have discussed? From that states, whatever the process is in ready, ready means it is supposed to be executed. That type of processes it will select. So it will select that type of process for what? For execution. So that is the short-term scheduler. Next one is medium-term scheduler. And it will reintroduce processes into memory for continued execution. That is nothing else than these are the differences or comparison between long-term scheduler, short-term scheduler, and medium-term scheduler. And these are three levels of scheduling in the operating system. Okay. Now this is about the process scheduling. The process scheduling will have the stages like this: job, these are the schedules. And this is the stages of the scheduling, process scheduling. Job queue, ready queue, CPU. Then we like to I will input output waiting queue. Then we'll go for IO states. Then in the ready state, again it will go to CPU. This is the process scheduling all about. The next one is CPU scheduling. The next topic is CPU schedule. This we already discussed long-term schedule, short-term schedule, mid-term schedule. And this is a comparison. Next one is CPU scheduling. You will see the next topic is CPU scheduling. CPU schedule. And before this, we discussed the process scheduling. The process scheduling we have discussed. What are the stages of the process we have discussed, and the levels of the process scheduling. That is types of the process scheduling we have discussed. Those are the 3 points we have discussed with respect to the process scheduling. Now it is CPU scheduling. Our thesis is CPU scheduling. Yeah. Now, CPU scheduling is a task that is performed by the CPU. So, what is a CPU? Central processing unit. Okay. Now, this CPU scheduling. The CPU scheduling one of the module. Can understand. And this CPU scheduling job is it is this CPU scheduling is performed by the CPU. Okay. And that decides the way and order which the process should be executed. So who will decide that the CPU is decide and what is the way of scheduling or executing and what is the order of scheduling, it will decide. The CPU decide. Okay. Now there are two types of CPU scheduling is there. One is preemptive and non-preemptive. We will discuss them in detail. Now coming down. Now what is CPU scheduling you see here? Now CPU scheduling is a setup. A process is essentially just a set of instructions or a program in execution. That is what we understood already. Okay. Now it is having the this is the process. See here CPU is there. Let's see here. This is a job queue. From the job queue, the process is going to ready queue. And from the ready queue, it is going to CPU. So where we have discussed in the CPU scheduling, this part we are discussing. And this part we have completed. The process scheduling we have completed. Okay. Ready queue. And the CPU scheduling. In the CPU scheduling, if it is performed, then it will execute over. Then if it is not performed, it go to the waiting state. You see, this is a waiting state. And from the waiting state, it go to the IO acceptance, IO module acceptance. And from there, once it gets the IO confirmation, IO means input output confirmation, it goes to the ready queue. It goes to the ready queue. Okay. Now, now there are there are the types of schedulings are there under the four conditions. Okay. Now see here, the CPU scheduling is having two types we understood, preemptive and non-preemptive. Okay. Preemptive and non-preemptive. That we'll discuss in another topic. No? Now see here, what are the kind of terminologies we used in the CPU scheduling? What are the kind of terminologies we use in the CPU scheduling? One terminology we used is arrival time. Next one is burst time. Next completion time, turnaround time, waiting time, response time. These are the kind of terminologies we use in the CPU schedule. But in that depth we don't require. So this is about the CPU schedule. There are two types of CPU schedules. One is preemptive and one is non-preemptive. Now what is this preemptive? You see here. This is a preemptive. You see. Are you able to understand, right? Yes, guys. Are you able to understand what I mean to say? What I'm saying here? Yeah. Okay. So now we are discussing the types of scheduling here. CPU scheduling here. There are two types, preemptive scheduling, non-preemptive scheduling. So what is preemptive scheduling is the preemptive scheduling takes into facts that they could have a higher priority and hence they must be executed before the process that have lower priority. So what is preemptive means? Some processes have the higher priority. Example here is this is the memory. This is the memory. In this memory, there is a process is there. Let us take this process is on priority one. This process on priority two. This process on priority three. This is on priority four. Now, according to the numbers, we can say that this priority four is high priority. So when it is high priority, it will execute first. It will go to the CPU. It will go to the CPU. Okay. As soon as it receives the CPU, when it receives the process, okay, we see the process priority number that is a 4 and this also will send P. So based on these numbers, the CPU execute the highest priority process. So it will execute first highest priority process, then after next priority process, then after next, then after next. So at last it will execute the priority one. So here your number is 4. It is greater than the 1. Okay, it is not that first number is 1, 1 is greater, it is not. So it is 1 is lesser than the 4. That is 1 is less than the 4. That is the reason. The 4 will be executed first, the 1 will be executed next. So this is the preemptive scheduling. This is the preemptive scheduling. Okay. And remaining all are having so many other concepts, we don't require them. Next one, see that non-preemptive scheduling. Non-preemptive scheduling. So see, the non-preemptive scheduling, what is doing? The new process are executed only after the current process has completed its execution. So it always gives the priority to current process upon new process. So the new processes will not be executed first. First, what it does, it will execute the current process. Example, say in the memory it is having, the memory it is having 1, 2, 3 process. Let us take this is the new process. This is a new process. This is the current process. Okay, current process. So the CPU will execute this current process first. This is the CPU. The CPU will execute this current process first, then after the new process. So this is called non-preemptive scheduling. Okay. So that is the process holds the resources. Resources series what CPU time. So till its state changes to terminated. Okay, that means this current process to be executed, okay, to be executed so that the current process states will be changed. So what is the state? Once it is executed, it go to the exit state. Exit state. So when you go to the exit state, then it will select the new process to be executed. So that is called non-preemptive scheduling. So that is non-preemptive scheduling. Okay. Now see here, so that is about the non-preemptive scheduling. Next one we will see context switching. Context switching. Context switching. Now see what is context switching here is, this is a kind of method, or you can say method, or you can say technique. It is a kind of method which stores or restore. Okay, it can store and restore. Stores the state. Okay, the state in the PCB. PCB means process control block. Okay, so that process execution can be resumed from the same point at a later time. The meaning is, suppose this is the CPU, this is the CPU, and this is the process, this is the process. In the process, there is a process, other two processes are there. Now it is going to CPU time, it is given. Now with some reason, it is go to the, let us say, waiting state. It will go to the waiting state. Then next one will be go to the CPU time, and it will be executed. And once this process is executed, again the old process, whatever it is there in the waiting state, it will be resumed, means it will be continued wherever it is stopped. That is the meaning of this. Wherever it is stopped, from there it will start executing. Let us say we will watch the movie. Okay. After watching this point, we will stop the play. We will stop the play. When you click on the play again, it will resume it wherever you stopped again. It is not that it will start from the beginning. Wherever you stopped the play, and from there it will continue to play the audio or video. This is called context switching. So this is the context switching is a method is for multitasking. This is for multitasking operating system. If you understand, it is multitasking operating system. It is okay. Next one, see now see here context switch. Context switch is a mechanism to store and restore the state or context. The state or context of a CPU in process control block. Process control block here is what we can call it a PCB. Process control block. So that process's execution can be resumed from the same point at a later time. For example, just now we understood. So that is the, this is the video. This video will be, you watch it till here, then you stop the play. They stop the play. And when you click on the play, it will resume from, it will start from here itself. It will not start from the beginning. So that is called context switching. Now going down, now see here, see this diagram. Now the process one is there, two, and see here, this is a process two. Process one is This is completed. Again, process 2 is selected. Okay. Then process 2 is continued. Process 2 is continued. Again, the process 1 is continued. So it is switching between process 1 and 2. It is switching between process 1 and 2. That is called context switching. That is context switching. So the context switches are computationally very intensive. Okay, very intensive since register and memory state must be saved and restored. The wiki it is stored in the registers. Okay, so that it is able to access very quickly. Is able to access very quickly. Okay. To avoid the amount of context switching time, some hardware systems they give now two or more sets of processor registers. Okay. So what it will store inside that the following information can be stored for later use. Okay. So how they are able to access so quickly that based on some kind of information it is stored there. So what kind of information it is? One is program counter, scheduling information, and the base and limit register value, and currently used registers, changed state. So this is the kind of information is stored in the register. So based on this information, it is able to it is able to switch between these two processes very quickly. Okay, that is the meaning of this. Next one. So that's all about your CPU scheduling. And there are the process scheduler, different process assigned to the CPU based on the particular scheduling algorithm. There are some algorithms are there. Okay, these are the algorithms are there. First come, first served base algorithm and shortest job next one scheduling and priority scheduling and the shortest remaining time, round robin, multi-level. These are the kinds of process scheduling algorithms. Okay. This mathematical is not, it is a little in-depth for you it is. So cannot only CPU scheduling, what is the types of CPU, what is the two types of CPU schedulings and what is the context switch? Okay, how the processes change their processes or context between the multiple processes. So these are about the CPU scheduling. The next one is just a minute. Just a minute. Yeah. Next topic is semaphores. Next topic is semaphores. You see, here. Next one is semaphores. Now, semaphore has constantly uh, is a kind of disrupted students. Okay, wait a minute. Yeah. Now, the semaphore is which is essentially non-negative integer. Okay, non-negative integer that is used to solve some critical section problems. Okay, some critical section problems by acting as a signal. Okay, so what you can understand, the semaphore is a kind of signal, which is non-negative integer. Okay, non-negative integer, and that can be solved some critical section of the problems. Okay, critical section of the problems. So, okay, that is what exactly the semaphore. It is a signal. Okay. Now see here, see here. For example, there may be some, there are some resources. There are some resource. One resource is there. Resource like, just like you take it as a printer. Okay. There is a printer is there. Printer is there. This is a computer. Computer one and computer two. Okay, likewise. And this is the printer P. So printer is the resource here. Printer is the resource and which are shared by three different processes. Let us take this is one process, this is one process, and there is a one more process. Okay, one more process. And none of the process has a certain time can change the resource. So since that might mean the result of the processes sharing the same resource. Okay. So these three processes do not have what time they need to share this printer resource. They do not have one particular time. Okay, they do not have one particular time. So this is where the problem will arise. So now this process synchronization required some concurrent process. Okay, so that is the number of processes that are executing simultaneously. So these are three processes. Now these processes has to execute simultaneously. That is one after the other. One after the other. Okay. So all of them to this is called critical section. Okay. So they have to have some kind of time interval, time interval to access this printer resource. So as they do not have any proper time interval, that is the problem actually. This is the critical problem. Okay, this is a critical problem. To solve this problem, there is a concept called semaphores. So what the semaphores are having now? There is a non-negative integers are there. So non-negative integers are there. Now they will give one solution here. Now see your example. We have five resources, and one process using it. Okay, we have five resources are there, and one process is there. the five resources. That is one, two, three, four, five resources, and there is one process, P1. And the incrementing its value by one. Okay, increments its value by one. In the example, so that is process X. So if another process Y releases the same resources which is taken earlier, okay, and the resultant what that might be occur and the resultant would be 4. So instead of 5, they're having 4. Okay, this is one of the example of the critical problem. There are two types of semaphores are there. There are there are types of semaphores. So one is a binary semaphore is there. Next one is counting semaphores are there. So what is binary semaphore? See, this binary semaphore is having either 0 or 1. Okay, whereas semaphore is having what? Non-negative number. Semaphore is having what? Non-negative number. Non-negative, non-negative number. Okay, non-negative number. Whereas binary semaphore is having 0 or 1. If the value of the semaphore is 1, okay, it means that the process can be proceeded to the critical section. Okay. When the binary semaphore value is 1, the process can be proceeded to the critical section. Okay. That is the common section. And if the value of the binary semaphore is 0, that is 0, then the process cannot be continued to the critical section of the code. So this is the meaning of the binary semaphore. So binary semaphore is having two values. One is 0, one is 1. Okay. If the binary semaphore value is 1, that is 1, the process can be proceeded to critical section. Okay. And whereas if the semaphore is 0, then the process cannot be continued to the critical section. Okay, this is called binary semaphore. And whereas now see here, the diagram see the initial value is 1. Okay. When the value is 0, then the value is 1. Okay. So it is called when the value is 0, it is unavailable. Okay. When the value is a 1, it is saying what? Available. Next one is what? Counting semaphore. Next one is counting semaphore. The counting semaphore is signaling integer. So that can take any integer value. That can take any integer value. Okay. Whereas semaphore is taking non-integer. Binary semaphore is taking 0 or 1. Okay. And counting semaphore is taking any integer value. See the difference between all of these. Semaphore is taking non-integer value. Non-integer value. And a binary semaphore is taking 0 or 1. And a counting semaphore is taking any integer value. Okay. Now using these semaphores, we can coordinate access to resources. Okay. We can access what resources by using these semaphores. By using these semaphores, we can coordinate access to the resources. So here there are semaphore count is the number of resources available. So what is the semaphore is telling? The count is the number of resources. Okay. If the value of the semaphore is anywhere above zero, anywhere above zero, the process can access the critical section. Okay, that is shared resources. Meaning is what? I said here printer is there, printer is there, printer is there. Here there are processes are there. Process one, the process two, okay, process three. Now what is telling? If the semaphore is above zero, if the process number is above zero, if it is above zero, it is above zero, it will it will access the critical section of the process. That is, here they can access this printer. Any one sheet, it is not that all the processes are above the zero. Clearly drawn. This is process one, this is process two, and there is a common resource. This is the resource. The resource is what? Printer. The resource is printer. And this process one is greater than zero. This process two is less than zero. As this process C1 is greater than zero, it will access this resource, printer resource. So that is what the semaphore is telling. If any semaphore value is anywhere above zero, the process can access the critical section or shared resources. That is the mean. The, num the number of processes that can access the resources code is the value of the semaphore. Okay, did you understand this? See here, initial value is there. See here, initial value is 1. So here release counting is count plus 1. That count is equal to 1. Okay, this requiring count minus 1. Plus count is 0. You can see here. So this is a diagram of the semaphore. So this is what semaphore, two types of semaphore, binary semaphores and counting semaphores. So by using the semaphores, we can access the critical section of the common resource. We can access the critical section of the common resource. That is the meaning of the semaphore. Okay, remaining we will continue tomorrow class, next class. Yes.